Buenos días para todos y todas. Es un honor para mí, como bayesiano, poder presentar al profesor Carl Henrik Eck. Es una destacada figura en el campo del aprendizaje automático y el modelado estadístico. El profesor Eck es catedrático de Statistical Learning en el Computer Laboratory de la Universidad de Cambridge y también ejerce como profesor visitante de Machine Learning en el Karolinska Institute de Estocolmo, donde colabora en proyectos interdisciplinarios que integran inteligencia artificial y medicina. Su investigación se centra en el desarrollo de modelos probabilísticos que manejan de forma rigurosa la incertidumbre, permitiendo el aprendizaje eficiente a partir de pocos datos. Su trabajo combina enfoques bayesianos, procesos gaussianos y técnicas no paramétricas con un fuerte énfasis en la interpretabilidad y la utilidad práctica. Con una trayectoria internacional que incluye instituciones como UC Berkeley, el KTH Royal Institute of Technology y la Universidad de Bristol, el profesor Eck ha publicado más de 90 artículos científicos y ha contribuido a aplicaciones en áreas tan diversas como la percepción robótica, el diagnóstico médico y la predicción climática. Por favor, demos una cálida bienvenida al profesor Eck.
Thank you. Thank you very much for the introduction. It's a real pleasure to be here. I've been in Colombia now for a few days. I've thoroughly enjoyed myself. I was here when I was in my 20s, and now it's really nice to come back. I'm much older than 20. That you can figure out how many years I am now. So I'm going to give 3 sets of lectures, and we're going to start off today with a lecture to try and make sure that we're all on this roughly the same page. And the idea is that we're going to go through things that I hopefully think will be familiar to everyone. But I'm going to start off by telling a story. So it's a little bit washed out, but this here is Giuseppe Piaggi. So Giuseppe Piaggi was sitting he was a scientist in Palermo in Italy. And on the New Year's Day, so the first day of the year, 1801, he was looking at the sky. He was one of many doing this. And then he sees something, sees this thing. Finds this interesting, so he catalogues the position of this thing that he sees. The interesting thing is, over a few days, he keeps following this object, and he sees that it moves to the background of the stars. So that means it's not a star that he's looking at, it's potentially a planet. And as I said, he wasn't alone looking at this for this thing at that time. He was part of what was called the Celestial Police, which was a thing in Europe at the time. The reason why they were looking for this, or were trying to, why he was looking at the sky, was that there was something called, at that point in time, the Titus-Bode law. Anyone familiar with this? Good. It's not a law that exists anymore. But the notion was that we'd observed Venus, Earth, Mars, Jupiter, Saturn, and Uranus. And they have a very peculiar structure. So each planet appears twice the distance from the sun to the previous one, right? So that means there's a glaring gap here where there needs to be a planet, right? And as a scientist, discovering a planet is about as cool as it gets, right? So there was a whole group of people then called the Celestial Police. They had divided up the night sky in between them and said, you keep track of that, I keep track of that. So now Giuseppe was very excited. So he took a set of measurements. I'm sorry about the washed outness of the projector, but it doesn't really matter. So what he did, he recorded a set of measurements. You can see 1st, 2nd, 3rd, 4th, 10th of January, and so forth. And then, at this point of time, the planet disappeared. Giuseppe got ill, and he could no longer track it. So it was gone, right? So now, it took some months, and he published this in one of the first scientific journals in Europe. It was written by a Hungarian scientist called von Zach. So von Zach collected things and he distributed it out to everyone. So in about April, May, scientists across Europe have this table. And now the chase is on, right? So now, who's the first that's going to find the planet? So this is actually the article. I could have read this. You can see it, hopefully the slides will be distributed, but this is the actual article which says something, I'll read it from my screen. An important circumstance of astronomy has just occurred, no less than the discovery of another planet, 3 exclamation marks, right? Even 1801, people wrote it. So it's a super exciting thing. So now the task is to find this planet again. So what we have, this is the actual data of these 27 points, right? And now it's behind the sun. So we need to figure out where it appears, right? So it's a problem of fitting a mathematical object to data. So we knew that planets, I'm sorry, you can't, is there any way to get some more contrast on the screen? My slides are not really showing. So you see, yeah? Let's see if we can get this. Hopefully you don't need to see this, but the notion was that at this time we knew the Kepler's laws of motion. So we knew the planet worked on ellipsoids, right? So the task was now to fit an ellipsoid to a set of data. No one can do this. So lots of people came up with ideas. The planet's going to appear in June, July, at this date, at this position. The planet never appeared. So people started thinking, this Giuseppe guy, he's just a scientific fraud. He's just made up this data, right? So then into the picture comes this fella. This is Carl Friedrich Gauss. And this is Carl Friedrich Gauss as a 23-year-old. He was completely unknown. No one knew anything about him. He didn't know particularly much about astronomy. He was a mathematician. So what he did, and the problem that he tried to tackle, which for us is going to feel very natural, was that he made a calculation and he published these numbers. So November 25th, December 1st, December 9th or 7th, and these were the positions where the planet will appear. And then Franz von Zach pointed his telescope at this position in the sky and the planet appeared, right? So now, think about what this is, right? Go back 220 years. This must have felt like magic, right? Someone got data, a mathematician, did some computation, and then he predicted something out in the world, right? We think about how excited we are about what machine learning is doing at this point of time. I think this was exactly the same type of moment, right? So Ceres appeared. And this is actually a picture of Ceres. If we would have had better contrast, you will see some glints here, which some people say there's cities on Ceres. There's not. But maybe there might even be water on Ceres. So Ceres exists. Have anyone heard about it before? No? Okay. So this is either because you don't know this story, or that you haven't watched the sci-fi show The Expanse. Do you know about this show? There's a sci-fi show called The Expanse where this is actually there, where they talk about Ceres. So the reason why you haven't heard about Ceres is that Ceres is actually, it was demoted because it's seen as something that's part of the belt. So it's no longer a planet. But the cool thing, it appeared exactly where Titus Bode's law says it should appear. So what was the problem Gauss had to address? So the problem at the time was something like this, right? We're trying to fit a mathematical object to data, right? That's our task. So let's simplify this a little bit and say, instead of an ellipsoid, I'm going to fit a line to data. Great, I got 2 points, super easy, we just fit the line, right? Now, what happens if I got 3 points, 7 points in this case, right? It was an overdetermined system, right? At this point of time, before Gauss, people didn't know how to do this. This is all very natural to what we would do at the moment. What people thought is that clearly there's 3 possible lines. 2 of them are false and 1 of them is correct. That's how people thought about the problem of fitting mathematical objects to data. And of course, this problem just becomes bonkers, right? So the more points we get, which one of this is correct, right? And Gauss then took a fundamentally different approach to this. So, an overdetermined system means that we have more data than we have parameters, than we need to determine our parameters. Now, the problem with an overdetermined system appears when the model that we define, in this case, previous case, the line, or in the case of the ellipsoid, you see if we can fix this. Yeah. See if we can get some more contrast and maybe some less, a little bit less light. If you turn this one down, I'm assuming Brillo is light. Yeah, turn that down. Let's see if we can get a good photo. Let's go to this fella. Yeah, keep turning that down. Okay, let's see how that, oh, look at this. Now we're much better. Here we go. Ah, look at this. We got it. Thank you very much. Good. And now you can see the cities, right? Oh, scary stuff. Great. So the problem when we go on overdetermined system is that we got more data than we need to determine our parameters, right? And the problem arises because the model in the case of the ellipsoid or the line is a simplification of the world, and the data is therefore inconsistent with our model, right? And these inconsistencies can come from many different things. So, what actually did Gauss do? Well, do we know who this fella is? Aha. To me, this is the most important person in statistics and in machine learning. This here is Simon Laplace. So Simon Laplace was a French scientist, apparently a very, very arrogant scientist, but he had the right to be arrogant because he was right about a lot of things. He also has he lived to a very long age, and he lived through very turbulent times in France. He lived through Napoleon without managing to get his head cut off, which is quite an impressive thing for an important person like him. So, Laplace he gave a set of lectures, late 1700s, that were later put in a book, which is called the Philosophical Essay on Probabilities, which really motivated Gauss to do the work that he did to find the planet. So I'm going to read a passage through this. We ought then to regard the present state of the universe as the effects of its anterior state, so anterior, the previous state, and as the cause of the one which is to follow. Given for one instance an intelligence which could comprehend all the forces by which nature is animated, right? So someone that knows all the rules of nature and the respective situation of the beings who compose it, who knows the location, the parameter, the state of the world, an intelligence sufficiently vast to submit this data to analysis, an intelligence, if we want to simplify this, I got a differential equation, I know the state of the differential equation, and I got the capability of compute this, it would embrace the same formula for the movements of the greatest bodies of the universe and those of the lightest atom. For it, nothing would be uncertain, and the future as the past would be present to its eyes. What it effectively means that if I know everything and I have the possibility of doing computation, the world would just be like an open book. I'll just turn the next page, right? So this is one of the most misunderstood quotes of Laplace, because it led to a concept which is referred to as Laplace demon. So Stephen Hawking, among others, wrote this in his book, Does God Play Dice? This led to the idea of scientific determinism, which seems to have first been publicly expressed by the French scientist Laplace. This is completely wrong. People who write this have not read this book, because that statement that I said is on page 5. Now, if you read till page 9, you will see this. Well, Laplace says, all these efforts in search for truth tend to lead the human mind back continuously to the vast intelligence which we just mentioned, that supreme being, right? But from which it will always remain infinitely removed. So what Laplace is saying, the notion of this type of world, where everything is exact, where I can just compute everything, is impossible to ever get to. All the three things that he mentions, being able to know the state of the world, completely impossible. Being able to do computation on the state, completely impossible. To know the equations that governs the world, completely impossible, right? All our endeavors as scientists tries to get us closer, but we'll never get there, right? So, what he then argues for, so this is what the whole book is about, because this is true, we can either get to a stage which was fitting those lines and deciding which one's correct, or we just give up, right? We search for truth, or we just give up. Or, what he says, the curve described by a simple molecule of air or vapor is regulated in a manner just as certain as the planetary orbits. The only difference between them is that which comes from ignorance. Probability is relative in part to this ignorance, in part to our knowledge. So he introduces the concept of probability in terms of thinking of this thing. Because as long as I can quantify my knowledge about something, right, I don't need to be completely certain or completely ignorant. A probability allows me to quantify how much I know and how much I don't know. And then he writes a whole book called The Theory of Probabilities, where he gives you all the mathematical framework for actually doing this. So, let's then look at what Gauss did with the philosophical ideas from Laplace. So, we have this overdetermined system, right? If I got lots of ice, right? We were trying to fit the line. I got two variables that I want to fit. I got an input and an output, and in this case, I got more than two pairs of y and x, right? So what Laplace then, or Gauss would argue for, is that this system is that system that Laplace would say is just naive, right? This implies truth, right? Instead, Laplace says, I'm always ignorant in this. And what I'm going to do is that I'm going to, for each relationship, x to y, I'm going to add a variable, called epsilon in this case, which parameterizes my ignorance, right? And then, what specifically Gauss did, he didn't formulate the Gaussian distribution, Laplace did. He said, well, what am I going to do? I don't know this variable, and I got 1 degree of freedom to every equation. I've now created an underdetermined equation system, but I'm going to parameterize and quantify my uncertainty about this, and in this case, he put a Gaussian distribution over this. Okay? Do you know why Laplace, or how Laplace derived the Gaussian distribution? Do we know why we always work with Gaussians, except for the math is very nice? So, Laplace argued for, if I don't know anything, I should be maximally ignorant, right? And the Gaussian is the distribution, the closed form distribution, that have maximum entropy. So it's the thing, if you want to maximize your ignorance about something, you should be Gaussian about the problem. And that's how Laplace derived this. He looked for something that has the slowest falling tails, but that still integrates to 1. And that's a Gaussian, and that's how we proved that. Great. So, if we look at then what this does, if we try and think back to the philosophical object that we talked about, I have some data points. I have some ignorance about this data point. I try and remove this ignorance so that I can fit a function to it, right? Now, the model that appears from this is just this classical probability model. If you make this Gaussian, we're going to talk a bit more about this, it it will look something like this. If you do maximize W for this thing here, you will get the solution that Gauss got that found the planet, right? Okay? So the key thing, the key message about this thing is the notion of I have some data which tells me something, I have some scientific models that tells me something, they're both a mismatch of each other, they don't say everything. If I match them together, I need to parameterize my ignorance about the problem. If I do this, fantastic things like this could happen. So, what we're going to do today is that I'm going to try and make the arguments that I tried to do now much more concrete. Hopefully these are things that you've seen before. We're effectively going to spend a lot of time talking about least squares, right? So not rocket science. The reason why I want to do that is I really want us to get philosophically on the same page. So then tomorrow, we're going to ramp up things really quickly, but it's not going to feel like it's quick, because the philosophy stays exactly the same, right? So what we're going to do tomorrow is we're going to talk about Bayesian non-parametrics, which are models that have infinite number of parameters, which are really interesting. And then on tomorrow afternoon, we're going to use these models in order to do several different types of computation. We're going to do statistical emulation, where we're going to look at the problem of optimization. So we're going to do something called Bayesian optimization. And then we're also going to look at, you can be uncertain about lots of things. If you buy into the principles that I give you today, we are going to look at how you can be uncertain about the concept of computation. So I'm going to show you how to do Bayesian inference over computation. This sounds all very weird, but hopefully, if we get today, then all of this will just be the same. I'm going to just be repeating myself with new mathematical objects, right? Does this sound good? Cool. And if you got any questions, please stop me, right? If I just keep going blabbering on for an hour and a half, we're going to be very tired, right? So please stop me, ask questions, and we'll get further. I'm just going to... Sorry. How do I do this? Great. So, oops, microphone. Perfect. Cheers. So now we're going to say, even though the example I gave you first, I think is really the first example of machine learning, 1801. Might have been things before that, but really the principles of that example is guiding principles for how I work, and I think fits a lot of the work. But now let's think about what machine learning actually is. Machine learning is inductive reasoning. In inductive inference, we go from something specific to something general. So I see a few set of points, and I want to generalize that to say something elsewhere. We make many observations, try and find a pattern, we try and generalize this pattern, and infer an explanation or a theory. So let's look at that. So here is the specific. I've got a few data points. I know at this point it's this. Cool. What I want to do is that I want to say something about the general. So I want to ask a question, what is the y value here? What's the y value here, right? We do that by building some form of theory or an explanation that says, oh, these are all combined by this sinusoidal. Now I can say something about everything, right? Great, super easy, we get that. The problem that we deal with is this. In inductive reasoning, unlike deductive arguments, allows for the possibility that the conclusion is false even if all the premises are true, right? What I mean by that is that this green function is exactly the same on all the data points, but it's different at all the other data points, right? It's only the same here. And now, the thing which is often, we'll talk a bit more about this, what's referred to as the no free lunch of machine learning, is that I can find, used mathematically, there's functions that passes exactly through these data points that takes any value between minus infinity and plus infinity here, right? Which tells me whatever I fit to this, I can give any possible explanation anywhere else, right? This is the problem that we're always fighting. So in order to address this, we need to add something more than just data and a mathematical object, right? We need to add assumptions, hypotheses, or beliefs. So very often, this is exactly how the scientific principle works, right? We start with some hypothesis. Oh, I think it's a sinusoidal. I test it. Oh, great. It fits my data. Then I might try another data point. Does it fit that as well? Now I've got evidence for this hypothesis maybe being true, right? And now if we put that into machine learning lingo, we've got data, we've got model. Through computation, I'm allowed to do a prediction that I can evaluate. Effectively exactly the same objects as in the scientific principle. So, I just wanted to hint at this as well. So one of the tricky things is that if we just look at predictions, if we don't care about the beliefs that we put into the system, you'll see this in my talk in the afternoon, we can get in real big trouble. There's a fella called Noam Chomsky, who I think we all know, partly because of his political things, but he's also a famous linguist. He said this thing, there's a notion of success which I think is novel in the history of science. It interprets success as approximating unanalyzed data. And I think this is a really strong statement, because what it effectively says is that I don't need to care about the hypothesis that I put in as long as it predicts the data. And really what we should work as a scientist is saying, I assume this, and now this happened. That somehow validates what I said when I came in. In order to do that, we need to know what we put into our systems. So, now, how do we do that in a machine learning system? So, I'm going to try and do a little bit of statistical learning theory here. So, if you want to divide up the elements a machine learning system works with, I have some form of hypothesis space. So when I'm fitting that function before, if I say it has to be a line, all the lines are my hypothesis space. If I say it has to be all polynomials to degree 3, that's my hypothesis space, right? So H, calligraph H, is the space of hypothesis. Then I have a learning algorithm, and the way I think about the learning algorithm is this. So here I got my parameterizations of, say, different lines, slope and intersection. My learning algorithm is the thing that navigates this, right? And I can avoid certain regions by putting beliefs into my learning algorithm to say, just don't go there. Okay, so I don't see that, right? Then you got our data set, our finite data set. So in this case, tuples x and y. And then this data follows some form of distribution. So some distribution in the product space xy. Okay? And then I have some form of loss function. So I have some function that says, if I take my hypothesis space A, apply my algorithm A on that, on the data S, this will return a function, some form of predictor, which I can then evaluate on a point of data, which will give me some scalar value where small is good and big is bad, right? So this is some form of measure of goodness. Okay, so what would then machine learning be, or statistical learning be? Well, the sensible thing that I would want to do, right, is that I can formulate an error, which would be the expectation of the loss, right? This would be the sensible thing. This is exactly what I want to have, right? So I evaluate the loss function at every data point, and I take more of data where I have a lot of it, where the data is probable, right? So I can evaluate that. It would just be this integral, but clearly we can't do this, right? Why can't I do this? Why is this absolutely impossible to do? It's impossible to do because if I knew the distribution of the data, I wouldn't really have anything to do, right? I don't know the distribution of the data. I only have S. I only have samples of the data. I don't have the full distribution. If Giuseppe Piaggi had the distribution of where the planet would appear in space at any point of time, he would just go and evaluate it, right? He only had a set of points. So we can't compute this, and this is what's known as the true risk. Instead, we have to compute what's called the empirical risk. Because I got X and Y pairs in a finite set from S, so what I do is that I just take the average error of these, and these are called the empirical risk. So now, the no-free lunch, more specifically that I talked about before, that I can fit any function that goes exactly through the data points that can take any value along those lines. More specifically, you can think about it as this. We can come up with a combination S, A, and H that are equivalent under the empirical risk. They can, let's just assume they all go through the data. So the empirical risk is always 0, but makes the true risk take a completely arbitrary value, right? So go back here. Let's go back here. The empirical risk of green and blue are exactly the same. They're 0. Oh, the empirical risk. The true risk, if the actual true function was the blue one, is humongous for this one, and it's 0 for the blue one, right? But when I do machine learning, I don't know if the blue one or the green one is correct, right? And that is what's called a no-free lunch. And this is, whatever anyone says, the thing that we're all fighting, right? Great. So, if I now have these 3 objects, A, H, and S, these are really the things that I can play with as a machine learner or a statistician. Now I want to put in constraints on them, right? I want to limit this incredibly underdetermined system of equation or problem that I have to make it somehow well posed. So let's think then about the first object, A. So this is very common in modern neural networks, for example, and I'll talk a little bit about this in the afternoon, where you put in constraints on the learning algorithm, right? So I think a little bit about this as, if you've seen Monty Python, there's a sketch called The Ministry of Silly Walks, where John Cleese is walking around like this in funny ways. That's a little bit how we design gradient descent algorithms, right? I also think about it as wearing clown shoes. Very often we've found that when you do stochastic estimations, so you do a worse estimate than the true estimate, you do better. What that leads to, I think, is to go an energy landscape that you're trying to optimize. You've got these very narrow valleys. You don't want to land in them, so you put on clown shoes on your algorithm. Now you'll never fall into them. Okay? Even though I made fun of this, it's clearly a very valuable approach. The other thing you can do is you can somehow manipulate your data. This is often called data augmentation, so that your data represents something. So an example of this would be, I want to learn an image classifier that can separate my mum and her dog, right? So I got 2 classes. Turns out if I take an image of my mum, or if I take my mum and turn her upside down, she's still my mum, right? I don't really have many images of my mum upside down, right? But I really want to learn to teach the function that I learn, that if you rotate an image, it doesn't make a difference. That I can do, right, by just taking all the images I have and just rotating them, right? To force the model to not pick an explanation that I don't want, right? Well, the final thing is actually looking at the hypothesis space itself, right? So thinking about what type of functions, classifiers, whatever it is we're looking at, do I want? So putting constraints directly on the space of functions. This, to me, is the most natural thing, because this feels like in the scientific principle, this is when I really make a statement, I think planets move like ellipsoids. You go out and test it, it seems they do. Great, now I somehow support the planet moves like ellipsoids, right? If I did the other stuff, it's a little bit more shaky, it's a little bit harder to get an interpretation. So what we're going to do in this lecture, we're going to think about a really simple example of this. We're just going to do lines, and then tomorrow we're going to do crazy stuff where we look at the distributions over the whole space of functions. Great. So, hopefully, I've tried to argue that if we think about machine learning according to these components, it is very much the scientific principle as a computational object, right? So now we're going to look at how do we make hypotheses. And, importantly, when I made hypothesis, which we're going to encode in our model, how can I, through compute, get an updated hypothesis that I can check evidence for that now either supports it or not? Okay, we happy with this? Great. So, whoopsie-daisy. I got one more thing that I wanted to say on this. Okay, so we talked a lot now about the model, and that's where we're going to go. So how does data fall into this? Well, if I take this thing, if I have a space of functions, clearly this point, if I say the function has to pass through this, it constrains it a lot. So I add another point, I get more constraints. I can add an enormous amount of points, and it just keeps adding constraints, right? And I like to put that on this Pareto front, which some of you in the audience have seen before, where I think about, on this axis, I got volume of data, okay? And in this axis, I have constraints on my model, right? So now, let's take the extreme case, where I've seen everything I'm ever going to see, right? Now, you don't need a model, right? You have a lookup table. If anyone asks you a question, you already know the answer. You just look it up and you give it back, right? You can predict everything. If you knew, if you were actually this entity that Laplace talked about, you have perfect knowledge, you don't need the data, right? If anyone asks you a question, you just put it in, compute, and give them the answer, right? This is not machine learning. That's not machine learning. Machine learning sits somewhere here, right? It's where my knowledge is not sufficient, right? And my data is not sufficient. And the task is to combine these two together, right? And now, of course, the more data I get, the less knowledge I need, and vice versa. You see the interplay between these, right? If I specify I want to fit only lines, now I've introduced an enormous amount of knowledge, right? Lines is a very small subset of the space of functions. I need 2 points, right? If I take some batshit crazy polynomial with 100 million parameters, now you better have a lot of data because your model assumptions are very, very small, right? Do you see this interplay? Good. So, doesn't really matter. However many data points, there's still a point in between them, and no free lunch tells me I can find a model that gives me any value between the two. So, now we're going to try and encode our beliefs, and we're going to encode beliefs using probabilities. And the way we're going to encode them, we're going to think about these as Bayesian probabilities. And what this means, don't think about this as frequencies. So what I mean by this, if I got a parameter, x, and I read off the density value, p of x at this point, it tells me this is how strongly I believe the parameter is to have that value. It doesn't mean that if x is a trial that I can redo, if I redo it 100 times, this is the histogram. That doesn't mean that at all. It just means that my belief in the variable is this, right? That's the difference which we talk about, the Bayesian notion of a probability or a frequentist notion of probability. Let's not get into this fight when we don't have beer in front of us, right? That's one of my rules. So, if we then think, now you can't see the colors, but these should actually match the scientific principle I had before. So I tried to do it. Now, we can think the only object we really need is base rule. Anyone who knows probabilities knows the base rule shouldn't be allowed to be called a rule. It's the simple consequence of the product and the sum rule applied once, but mathematically it's an utterly uninteresting object. Semantically, it's very, very interesting. So what this says is that this object here, we're going to refer to as the likelihood. It says, y is my data, theta is my parameterization of that data. If I knew what the parameter would be, this is my belief over what y should be. That's what this thing quantifies. So in some sense, how much evidence is there in the data for a specific hypothesis, right? So that's what this quantifies. Then I have the prior, which is this one, and that says, what do I think? What are my beliefs about different hypotheses, right? That's what this thing quantifies. So if it's high, it's a hypothesis that I really like, right? And then you combine these objects to get the posterior distribution, which tells me if I've seen this thing, what do I now believe the hypothesis should be, right? So that's that notion. So for example, you can take this ID, right? I don't believe the Earth is flat. I don't. But now you're trying to convince me that it is. And you do a damn good argument for that the Earth is flat, right? So now I have a very small prior belief on this, but Juan's giving me some really damn good data, right? If the Earth is flat, oh yeah, that makes sense. Oh, that makes sense. Oh, that makes sense. Now I'm going to get an increased probability of me believing that the Earth is flat. Now, I believe the Earth is a sphere. I need very, very little data to alter my belief, right? And this is the thing that this thing balances. And the bottom part of this thing here is often referred to as the evidence, which is if I take all my beliefs, the sum of all my beliefs and how much I believe in them, how well does that set represent the data? Okay? So, just to show you this, another way of thinking of what we're doing, the bottom part here is the really important object, because this is the thing that marginalizes this. This is the thing that gives this a scale. So, what does this integral do? So, often it feels a little bit confusing what this integral does. So stop me here. I just want to try and give some intuition of this. So if you think of what this is, I got a parameter space. Oh, let's for once say I got one-dimensional parameter here, right? It's called that theta. Now I have a certain belief. Let's say that that's the slope of a line. I really don't believe in these high slopes, right? I really have my belief down here at the slopes that are very shallow, right? So my probability distribution looks something like this. That's my belief, okay? Now, d theta is the canonical measure over this space theta. So the only thing it does when we were taught integrals, right? It chops up the space in equally big parts, right? That's what it does, infinitesimally. Now I take p theta, which is another measure. The way I like to think about this is that it takes this thing and creates a new measure. It creates a measure d transform theta. And the way it's going to transform it is that this space, where I have all my belief, which was a very small part of the parameter space, is going to stretch it. And this part over here, which I didn't believe in at all, is going to compress it, right? So now I have a representation that reflects my belief. So now, if I just toss a coin in there, right, the coin will land, or a stone. The coin, if I just uniformly throw it, will land with a probability that reflects my belief. That's the parameter I'll get back. If you want to see a sketch of how this works, right? So say that this is my belief over the parameter theta, right? Now, what I want to transform this to a parameter where if I just look uniformly, if I take the canonical measure and just chop this up, it will reflect my belief. This thing does exactly this. If I take this curve, which is the cumulative distribution, if I draw any point here uniformly, push them through this function, I'm going to get this distribution, right? That's just the transformation of measures, right? And that's exactly the only thing marginalization does. It just reparameterizes a parameter to reflect how you believe in this parameter. It gives parameters that you believe in more space, and parameters you don't believe in less space, right? Cool? Does that intuition make sense? Okay? So, if we then show these objects graphically, so now I have exactly this model that I had before. I have a line that only has one parameter, so it only has a slope. I have a likelihood function that basically says, if this is my parameter, I think data is likely to lie within this. If this is my parameter, I think the data is likely to lie here. Here are three different beliefs. The red one, I believe that the parameter, the slope, is negative, and I got quite a strong belief over that. The blue one, I believe they're positive, got a little bit less strong belief about that, and I got this very vague belief in the green one. If you now look at the evidence, which is the integral over this space, this is what the integral will look like. And when we put this thing here to normalize it with, what effectively that does, it is like taking a transformation of this green thing to make this whole space equally green. And the way I do this is, or let's take the red one, to make this equally red, is to make this part of the space much, much bigger, and this part of the space, which also has some red in it, compressed. And that's how the notion of marginalization. Good. So I'm not sure if I managed to convince you with this, but this is the only thing Bayesian probabilities do. We're going to see an example of it now. Laplace said then at the end of his book, one sees from this essay that the theory of probability is basically just common sense reduced to calculus. It makes one appreciate with exactness that with accurate minds feel with a sort of instinct, often without being able to account for it. It's an absolutely beautiful book. It's free, it's 100 pages long, contains very little math, just grand statement from a French mathematician, right? It's a beautiful book. So, we reasonably happy? We're okay? Yeah? Cool. We're running quite quickly. I was hoping for a bit more questions. So do we have any questions on this? Because now I want to do the concrete example where we take all these principles and put them into a very simple example that I think you've all seen before. I hope you've all seen before. And with that, I want to just nail down these notions so that tomorrow we can just crack on with some really cool and novel stuff. Yeah? So any questions or thoughts? No? Okay, with all this philosophy. Great. So let's just think about linear models then. So we're going to look at two different types of models. So we got a linear model. In this case, it's a linear function, which means that it's linear both in its parameters, W, and in the data, right? So this is something that will in the end generate a line, right? I can also, of course, do a linear model, which is linear only in its parameters, but it's non-linear in terms of the functions. We know this from splines, basis function, if you work with kernel methods. All these things are linear models. They just use basis functions. So the way to think about this is that you would just take an input value, you would evaluate it under this non-linear basis, and then you would generate a linear weighting of these, which will give you a non-linear function, right? Does this make sense? Great. So let's take the classical case that we had before. So our task here is that I have been given some data y and x. They have this relationship, so it's just a line. Now I want to take some data, right? So I want to take some data, I want to take hypothesis, and I want to test this hypothesis, right? So our tasks then, which are going to be the same throughout the 3 lectures I give, we're going to define a likelihood. So this is a modeling task. That means we need to think about what output do I consider likely under a given hypothesis, right? So the questions the Gauss had to answer, given this data point, what type of measurement errors do I think Giuseppe did, right? Personally, I would think his first data point was on New Year's Eve. I always have a few glasses of Prosecco on New Year's Eve, so maybe the numbers that I write down are slightly worse than on another day, right? Things like that is the questions that we need to take in. Then we need to define our assumptions or beliefs over the hypothesis space. So this is also a modeling question. So that means, what types of models do I think are more probable than others, right? What are the things that would really surprise me if the data supports? And what are the things that are like, yeah, cool, I kind of knew that, right? So I need to somehow parameterize my knowledge. And then comes then the computational task. How do I mix my beliefs with my new observations? So that means I need to formulate a posterior. And this is a computational task. And what we'll see tomorrow, everything we'll do now is in closed form. Tomorrow is not going to be in closed form anymore. We're going to have to do approximate computation on this. And then finally, I want to predict using my new beliefs so that I can go out and test this. And that means I need to formulate a predictive distribution. So if we can do all these steps, then we're kind of going with this framework. So we're going to follow exactly what Gauss did. So I'm going to say I got observations. I have a function class here, which is lines. And I'm going to say there's some discrepancy which parameterizes my ignorance about this. It could be that it's actually not lines at all. Or it could be that these measurements are noisy and so forth. So I'm just going to give an additional parameter y here. And I'm going to say that this is a parameter that follows a Gaussian distribution. So I make an assumption of this. So now, what we can do, coming back to exactly what we showed before, what this means is that now you can look at the bottom. I move epsilon over on this side, right? So I subtract epsilon from y. Now I get a new y, and to that I'm going to fit the function, right? So I remove my ignorance, and then I can fit the line, right? So let's now build a distribution of this. So let's build a likelihood. I'm going to refer to this as noise now. Let's just say that the function is really a line. It's just that there's discrepancies between y and x because the observations are somehow noisy. So what we do, I'm just going to move wx to the other side, so I've got epsilon clear. I've already specified my belief over epsilon. Epsilon follows a Gaussian. So if this follows a Gaussian, that means by the equal sign, this side also follows a Gaussian. So I got y minus wtx follows a Gaussian. Now I can write the Gaussian out like that. And if this is true, epsilon is equal to this. I can just chuck this in as the thing I'm predicting to. Right? So now I got this type of Gaussian here. Now the likelihood function, the distribution that we were looking for, was the distribution that said for a specific hypothesis, and the hypothesis space here is the W's, then what will y look like? So I want the distribution where I only got y on this side, right? W and x are not random in this case. I want a distribution which only talks about W. Well, if you look at this thing here, right? That's just the Gaussian over y with mean WTX, right? So I can equally, if these things are not random, I can just move them over to this side. And now I got a distribution P of y comma x, right? So a Gaussian distribution, a likelihood that is completely derived from the notion that I made an assumption about the noise, right? We happy about this? Yep.
In other kinds of models that the noise doesn't exist, for example, in binomial or Poisson models,
Yep.
why is better here to use a noise
Ah.
and not use a distribution directly in y?
So this is very good question. So now I derived this distribution from a noise assumption, right? Now you can derive this from other types of assumptions as well, right? It's used, in this case, it comes very natural, right? Where I would say, I'm just gonna, and clearly, right? You can, I've made so many assumptions here, which I've clearly held back, right? I'm saying that my ignorance is additive, my ignorance is stationary. I've said loads of things here, which I tried to brush over to use, a cleaner message, and then you correctly pick that out. No, it's exactly right, right? But whatever I do here, this is the object that I need, right? And we can think of very many different ways of deriving this, right? Yeah? Does this make sense to everyone? I was just saying in this case that the absolute simplest thing we can do is just say that my truth generates something, and then I got some noise on that. And the noise here and here are exactly the same. They're equally probable, they follow the same distribution, and it's additive. This would, for example, not be true. So say if you're modeling vibrations in a car engine, for example, I would assume that your sensor, when the speed goes up, the engine starts revving, right? Your noise will be greater. This is not the case here, right? Epsilon does not depend on x, which would be the revisions of the engine in this case, right? Super good question. Yeah, but we get how I derived this, right? From a notion of talking about, I think my data behaves like this, or I have some additive structure that I want to remove to model this. From that, I can derive a distribution that looks like this. Okay? So now, what we can do, now we have a likelihood. Now comes my next assumption. I'm going to say, if I know W, right, then Y's in other places are conditionally independent of each other. That makes sense for a line. If I knew what the line was, right? If I know what the slope was, and I know x, right? So I'm looking what the line is. Knowing that the line is that over there doesn't give me any extra information, right? That means I can say that the distribution of all data, they're all conditionally independent. So I can formulate the likelihood of a chunk of data by just taking the product over those, right? Not independent. Clearly the y values are not independent because they lie on a line, but they're conditionally independent knowing the line, right? So I got that. Great. So now the likelihood is Gaussian, where the parameters that we're interested to learn about sit in the mean. And now we're going to do a leap of faith. Now we're going to do something just to make the math easy, right? We are going to pick a very specific prior on this. Prior that doesn't actually make sense, but I'm going to pick a prior so that we can do the computation and analyze this. I'm going to pick what's called the conjugate prior to the likelihood. So how many have heard about conjugate distributions? Great, we got a few. Perfect. I'm going to explain what they are. Conjugate distributions are like a dating site for distributions. So they basically means is that if my likelihood looks like this, my prior is of a specific, is the conjugate prior to this. The posterior will have the same functional form as the prior, right? And this is super, super useful for many examples. So you see this, if I knew this is the likelihood, this is the parameter, the conjugate prior for this parameter is also a Gaussian. That means that the posterior is going to have the same functional form as the prior, so it's also going to be a Gaussian, right? If you go to Wikipedia, there's a big page which says likelihood, conjugate prior, posterior, right? It's effectively a dating site, right, for distributions. That's how I like to think about it. Now, does this make sense? I would argue, you'll see this in my lecture later on this afternoon, this makes no sense at all for most cases. I'm just picking this so that I don't have to do lots of integrations because I'm not great at it. So, this gives you a very nice interpretation. I start off with this, but this is my prior belief parameters. When I've seen n data points, I get a new mean and a new covariance. So the posterior, and why is this so useful, right? So if I wanted to get the posterior, normally we use that base rule, right? I just have to compute this. That implies this integral. Integration is hard. Now, I want to avoid doing that integral. If I already know the functional form of this, I can do this. I know that this is equal to this, right? That's just base rule. Because I know this is also proportional to this. This thing here is the thing that makes this sum to 1, right? Is the thing, as we talked about, that normalizes the space, right? Does all this stretching and compression. Now, I know the functional form of this. So if I just multiply these two together, I can just identify the terms of a Gaussian on the other side, right? So I take the product of likelihood and prior, and then I just identify terms. If you want to see this, I'm going to give you a long derivation of all the Gaussian identities if you want to see them. It's about 25 pages of lots of equations. They're fun to do once. You can at least see them, but I'm not going to do them here, right? So you will just have to believe me that the mean, the updated mean, looks like this, and the updated covariance looks like this, right? Okay? We can go in, we can go in and analyze these a little bit more. So now I'm going to introduce use the parameter and make this so that we get some easy looking equations. I'm going to say that the weights follow an isotropic Gaussian. So I'm saying that there's no covariance between the intersection and the slope in my prior. Okay? And it has this term alpha, which controls the variance. So that means I get a posterior distribution that looks like this. Okay? Great. So if you haven't seen this, hopefully you trust me on the math being right. So now let's look what this actually means in terms of a real example. So I have a model, this, so a line, intersection plus slope, and then I'm going to generate data where I have an intercept of minus 0.3, and I got a slope of 0.5. And I'm going to add noise, which has that precision. So I'm going to add quite a bit of noise, okay? And now I'm going to place a prior, which is super wide, like a really big blob of a Gaussian. I'm not very certain about this, okay? So now what we can do is that we can say, here's my prior, I've seen no data. Now I can sample from this, so I draw some probable points, and I generate those lines. Lines everywhere, right? Great. Now we see one data point, and I can compute my posterior, which now looks like this. What are the cool things that have happened? Right, 2 really cool things have happened on this side. If we compare this to this, how is that thing qualitatively different from that? Yep, you're on it. First thing? It has rotated. What does that rotation mean? No, but you're on something really good. It's rotated. Remember this one here. This was an isotropic Gaussian. That means there's no dependency between the slope and the intercept. As you can see here, doesn't look like a dependency, right? Now I see one data point, and this is rotated. If you would plot this covariance, right, it means it has to have off-diagonal elements, right? Otherwise it wouldn't be rotated, right? Does that make sense? Does that make sense that it would have done that? It does, right? Because clearly the intercept and the slope are dependent with each other, right? If I have this line, right, and I just point it down like this, right? Now the intercept is somewhere here, right? I've changed where the intercept is. If I change it like this, now I've changed where the intercept would be as well, right? So we've modeled a dependency between the slope and the intercept. Great. So that we've extracted from the data. The other thing is that we can see the volume, the entropy of this Gaussian has become tighter, right? That means we're learning something, right? Our beliefs are now stronger, right? Great. Let's take another point. Cool. Same thing kind of happens. It gets closer and closer. We see some more data points. Great, great, great. When do I stop? I stop here, and for some reason, I don't get negative numbers on my plots, but we can see where this has ended, 0.5 minus 0.3, right? So we effectively recovered where the data was, right? Okay, this is a little bit of a silly scenario. So now let's do something else. Let's start off with a completely different hypothesis. So now I have an hypothesis that I think the lines have massively negative slope and a very positive intersection, and I'm quite certain of that. Now let's see the same data points again. So I see this. It says, okay, well, you've given me this. It kind of says something different than what I thought from the beginning, but you know what? I still believe in these negative slopes. See another point? I can make that argument. Now it sees a third point, and now it's really struggling. Now the data start overwhelming it, and eventually, if we would have plotted a bit more, well, 0.5-ish minus 0.3, right? So enough data overwhelmed it. So let's go back now to this thing that we saw before, right? We started off, in this case, where we had a set of knowledge. They were lines. They behaved according to this Gaussian and so forth. And then we eventually overwhelmed our belief with data, right? So we're actually not committing, if we think in a Bayesian manner, we're effectively not committing to where on this slope we are, right? Because eventually data will overwhelm us. So now there's a really important point with this that I wanted to bring up. So this example here is ridiculous. Why is it ridiculous? Well, you're being asked to fit a line with 2 parameters with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. This is not where we work. The more common thing is you work on some bizarre physical phenomena that requires you to get a data point out of CERN that's taken millions of pounds to compute. Now you get that one data point, and you're supposed to fit 50,000 parameters to it, right? That's a much more common scenario. So let's try and do that analogy. Let's go here. Look at this, right? I've seen, this is my updated belief. Fundamentally different, right? These are the 2 priors I had before. have seen the same two data points, the knowledge that we've extracted of them are fundamentally different, right? Completely different, right? Now, that means, and this is a really, really key point, any conclusion that you draw from a learning algorithm can only ever be done in light of the priors that you put in, right? Super, super important, right? We know the no free lunch, right? We know that I can give you any types of lines here, right? If I alter my prior, I can give you lines that gives this value in the middle any possible value, right? So now, as soon as someone gives you a result, any learning algorithm that gives you a result will have to have made an assumption. If you don't know that assumption, you can't interpret the results, right? And that's why it's so important to understand the assumptions and beliefs that goes into a system, right? Is that clear? That's like a super important. So my whole point of why I'm doing this, which I think I spotted from the introduction, that I'm interested in interpretable models, interpretability is key, right? And interpretability can only ever come from knowing the assumptions that went into the system. And I'm going to argue, and the things that we're going to see tomorrow is for the interpretability coming from placing these very strong distributions over function spaces. Great. So, last bit. I know I'm in a statistics forum. So what's the difference between statisticians and machine learners? Nothing, right? We do exactly the same thing. Statisticians are much better at math. We're allowed to be a bit sloppy. Now, my colleague says this. The difference between statistics and machine learning is that the former cares about parameters, i.e. interpreting posterior distributions, while machine learners cares about prediction. So, let's then do the predictive distribution. So, in this case, say if I learned something, alpha and beta, that was the noise that I made an assumption about, that was the prior on the weights. Now, if I've derived this posterior, if I now want to predict, I don't care about the parameters, right? So I want to average them out. So I integrate the likelihood so that I now can predict over y star, given that I've seen two sets of data and I've learned and I've set these parameters. Now, this just looks like this. I have a point here. This here is the predictive distribution. It effectively says, you give me 1 point there, I think the line can wiggle like this, right? I see another point. Now it's a bit harder to wiggle. I see a few more points, dunk, dunk, dunk. And here is now my predictive distribution, that where the beliefs I put into the system would say, I think data lies between here. If you see that, you're supporting the hypothesis. Great. So, now, where are we on time? Oh, we're quite good on time. We're going to have about 10 minutes of questions, so that's good. So, now, it's as a hint for tomorrow. Let's just take things that are linear only in the parameters, but non-linear in the functions. So I take some form of basis function, a non-linear basis function, and then I do linear combinations of these, right? So my parameters now are weights of these basis functions. Now I can do exactly the same thing. My code for this is exactly the same thing as the previous one. Let's say I take one basis function. This is my predictive distribution, absolutely awful, right? In this case, I haven't learned the noise, so I've just fixed the noise. That's why it doesn't even do anything. If I take a few more, now how many do I have? 3, starting to look quite good. These here are the weights of 4 it is. 1, 2, 3, 4. These are the weights that I get. I can do whatever that now is, 10 maybe. I can do this. I can do this, right? When do I stop, right? This looks nicer and nicer and nicer. Try and interpret this, right? It makes no sense at all, right? What we're going to do tomorrow is to say, what if we take this to infinity instead? We're going to look at linear models where the basis function set is infinite. And it turns out, mathematically, infinity is much, much easier to work with than very large numbers, right? And that's true for a lot of things. So, brief summary of what we talked about today. There's a lot of philosophical nonsense for telling you about least squares, right? You know, history and Laplace and all sorts of things, right? Effectively, I told you something that we all know inherently. I told you, if you get three different things and are trying to decide between them, you take an average of the three, right? If you want to measure something, if you're going to cut a bit of wood, the saying at home is measure twice, cut once, right? That's just natural. It wasn't natural. The important thing was not to tell you about least squares. That was completely irrelevant, actually. Least squares was just an example of this. It was trying to tell you how I reasoned to get to the point where we ended up with. And now, my hope is that the reasoning I've now built up should stay completely consistent during the next two lectures. But now we're going to look at much more complicated models, but I don't want you to get confused by the models. If you can see by the end of tomorrow, oh, Carl's just repeating himself. This is the fourth time he's saying exactly the same thing. Then that's really cool, because that means we've got a consistent narrative of thinking about statistical modeling, and that's really beneficial. So, another thing, you just wanted to hint at this is normally the case where people are shown Bayesian statistics in the first one, coin tosses, right? I just wanted to hint at a slightly different thing. With that, you can exactly do this experiment yourself. So this is you saying, I have a belief that I got an unbiased coin. The actual coin is ridiculously biased. Now I compute my posterior. I do the conjugate. You have a conjugate relationship here, beta Bernoulli. Now you can see, exactly as in the linear regression case, I see enough data. Eventually it would overwhelm me. What I wanted to hint at was this very weird case. I have an absolutely nearly certain belief that the coin is biased to always say heads. And the real coin is actually here. What happens when I do this? A really cool thing happens. So, to the point that you were making before, with the Gaussian, we did a linear regression. You saw that we shrunk the mass the whole time, right? We were learning more. Here in this case, you've got this really nice thing, which I think is a very human notion. We get more confused, right? This is effectively what's happening, right? My entropy increases. And we have this all the time, right? When someone's trying to tell me something really hard, they first try and break down the things I know, which are usually wrong, right? And then I get like more and more confused about it. And then I start learning, right? Super, super simple. You get exactly the same characteristics out of a normal posterior distribution. Cool. So, that was basically the end of what I was going to talk about today, and we'll have a much more of the same thing, but in non-parametrics tomorrow. Great. So now we got quite some time for questions. About 10 minutes?
Tenemos espacio para preguntas. ¿Quién tiene alguna? Si alguien las quiere hacer en español, yo haré mi mejor esfuerzo por traducirla.
In your experiments, we could say that with enough data,
Yeah.
we always get to the same result?
Super good question. You pointed to a thing which I'm going to talk about this afternoon. No, it's a really good question. I want to bring it up with everyone here. So it's a really good question. This is how we're taught this thing. And actually, because that's how this is how you convince people with these things, which says that effectively, oh, it doesn't matter what prior you set, because eventually you'll get there. That's not true, right? The simplest thing where it's not true is if I would have put 0 probability mass here, right? Then it won't be true. That's the trivial case. But the other case is that when we start getting very high dimensional models, there's effects of high dimensional statistics that means that this is not true, right? Which is actually quite complicated. And also, there's an assumption in the Bayesian framework which assumes that the true model has non-zero probability mass. And that's also very, very rarely true, right? It's very, very rarely true. Ask a physicist, are you guaranteed that this physical phenomena has this parameterization? They can't tell you that, right? So, there's a lot of subtleties that happens to this. This is a bit of a tricky way to convince people. In this case, yes, it works. The other thing I wanted to comment on, look at this, right? I'm estimating one parameter. How many lines is that? That's one coin toss. It's a bit silly, right? I shouldn't even be Bayesian about this, right? You take it's a silly thing, right? Yeah. But what I could do, which is the more interesting, which is the more interesting thing, is this hypothesis testing thing, right? So think about it as a means of, your hypothesis was that it's always heads, right? Now you toss a coin 4 times and you say, nah, it's not. Invalidate that, make a new assumptions. Maybe you start here and you do 3 and it's like, oh yeah, now this all fits. Cool, that hypothesis is probably right. So I more think about it as hypothesis testing than the thing that would get me to the right model. Yeah, exactly that point. Yeah.
So I'm probably getting ahead of myself, but in terms of the confidence and beliefs from setting the probability distributions for the likelihood and the prior,
yeah.
How does that change with non-parametric assumptions?
Yeah,
so it increases the confidence, it decreases the confidence, or like?
Super interesting thing. You can actually, so I can formulate non-parametric priors that are really, really tight as well. So they would put probability mass, it's just the hypothesis space is infinite, but the place I place the distribution, I can parameterize that in such a way so that it's really, really narrow, right? So there doesn't necessarily need to be, oh, you're increasing your space, now you end up being more vague, right? It doesn't necessarily, but with parametric models, that's nearly always true, right? If I would have added a quadratic term to our linear regression, right? It just would have gone slower, right? Because my hypothesis base is effectively bigger, so whatever I slump down on is going to cover more stuff. Yep. Very good point. Oh, this horrible thing.
Well, I have a question. So we rely a lot on data. So when data is not correct, do we have an approximation with measurement error models or something alike?
Super, super interesting point. So the thing we're going to talk about tomorrow afternoon is going to be active learning when we make data acquisition a part of the learning process itself, right? Which I think is a very important thing. Most scenarios, data is expensive, right? Except if, you do internet silly things like cat classifiers, right? There's as much as you can find. But if you're doing real science, you're going to work with someone that's like, oh, should I test this drug on these people? Well, that costs a lot of money, and it's you really want to evaluate. So now, if you get bad data in, right? So say there's a trial where something happened, right? You don't know. Can you quantify that so that you can remove it? Well, we're going to look at how to do that, and it's a super, super important point. Because most machine learning models can't forget. And it's a really annoying thing. And you know this as a teacher, right? I only got very limited time talking to you guys, right? I need to choose my data points very, very carefully to give my, I don't know if I did a good job at it, right? But I try, right? And now that's exactly the same problem. If I give you data that gives you an intuition that's wrong, it's really hard to extract that, right? So negative data can be very detrimental if you put it into a system and learn, right? It's like training a dog, right? If you give them food at the table once, you know, you're done for.
I do have a couple of questions.
Absolutely. Now comes the
first one. It's a comment. Thank you very much for your talk. It was very, very nice, and I hope we can get a copy of your slides.
Oh, absolutely.
They're awesome.
Yep.
The first part of the question is related. It's kind of philosophical. What is your take? What is your opinion on the model uncertainty? I mean, all this stuff works if you assume that you have a model that is generating the data, right?
Yep.
So, what is your point? What is your perspective on how to propagate uncertainty in the model?
Yeah.
Beyond, beyond Bayesian parametrics, beyond the typical Bayesian model averaging.
Exactly. So I think, I don't think there's anything in the framework that tells me I can't do that. It's very hard to parameterize those things, right? So now, one of the things that I didn't show, let me see if I can, no, I'll just forget that slide, but I can of course do model selection, right? I can test multiple models and then I can choose based on them. The element that you choose them from is the model evidence, right? So you want a model that explains the data, but explains as few other things as possible, right? That's the notion of Occam's razor. The object that measures that is the evidence, right? So you can effectively think if the denominator in that integral is going to tell you what's the probability of the data under this model. Now, I can have several different models and compute the same object. If one model explains everything, including the data, it's going to have to spread this probability distribution over lots of data sets. A model that only explains your data set and nothing else is going to have just probability mass there. Because they both have to sum to 1, you now pick the one that has the highest probability, right? That's how you normally do model selection. I don't think that's the answer you're after. It's more of the fact that can I parameterize an uncertainty of the model itself in there? And there's nothing saying you can't do. We do this with, what's it called? Ensemble models, right? You can kind of say that an ensemble is that, where you would have a probability distribution on the ensembles themselves, right? But it's more of a problem of the parameterization. How can I actually parameterize this object itself? If I could, and I could integrate, job done, right?
Okay, thank you. The other one is curiosity. You mentioned before the normal isotropic prior, that the normal prior with general M and the general covariance matrix doesn't make any sense at all. What is your take on that?
So my reason why it doesn't make sense will be on a slide this afternoon. I'll tell you about it already now, but basically what it means, if you think about a parametric model, right? This is a measure in the parameter space, right? So now if you think in the function space, which is the thing I'm interested about, right? So the difference, say that this has slope 0. Let's do the math easy. No, 0. And this is slope 1, right? The difference in parameter space is 1 between them, right? This thing has slope 1000, and this thing has slope 1001. In parameter space, those things are equally different. In function space, these two things are hugely different, and these two things are exactly the same, right? Now I've placed a measure which is effectively directly in the parameter space. And that's the problematic thing, right? To me, with those types. You would want to transform so that the thing that I actually care about, which is in the function space, and I can transform this, right? It's not rocket science to just have a transform parameters that actually get the right thing, right? And that's why I don't think it makes sense, right?
Okay, thank you. And the last one is like maybe something related with language. The scientific community is not comfortable with the word believe, you know, because of the context, maybe the religious context that it can take. Is there any other expression or idea you can talk about?
Exactly. Beliefs is a very tricky thing. So I often talk about constraints or assumptions. And I just formulate them as probabilities, right? Yes, don't talk, when you go out and talk to proper scientists, don't use the word beliefs, right? Because for some weird reason, it's a very odd thing, right? If you say you believe in something, very often that gives people a notion of distrust in you, right? To me, that's really weird. It should be the other way around, right? To me, if you tell me a fact, right? The fact doesn't tell me anything about me. My beliefs tell me something about me, right? And in having a conversation where you build trust, I really want to get your beliefs, right? The facts is just like, yeah, you live in Bogota, right? It doesn't tell me anything about, well, okay, forget that, but you see what I mean, right? But so when I'm having those conversations, which we often do, I always try and talk about the constraints, right? So if you talk to physicists, it's like, what are the symmetries of this problem? What are the constraints? Oh yes, speed of light. Oh yeah, that's a good one, right? That's a constraint. And then I talk about beliefs with the people who actually implement the stuff. Yeah.
Thank you. Any more questions? Ok, bueno, agradezcámosle a Carl por la charla. Gracias.
I've been told that these venues are, because we've got these multiple parallel tracks, I hope that there's going to be very clear evidence if I did a good job or not, because either I'm going to be here alone tomorrow morning or you'll all be back. So hopefully you'll all be back.
Buenos días, muchas gracias por su asistencia. Por favor, tienen que registrar la asistencia para el certificado a mano derecha.